Go into the next topic with respective to the second module, which is pertaining with scaling and small geometry effects and along with MOSFET capacitances. So the purpose of this particular topic is we need to shrink the size of the IC. When you're shrinking the size, you have to have a different dimension. So the dimension exists as it is, but you have to scale it. You have to have a parameter which has to be scaled. Normally we write the scale on the graph. So 1 centimeter is equal to 10 volts or 1 centimeter is equal to 1 meter. But that doesn't represent that it is 1 meter. Then when you go back and scale up, you do the reverse procedure. If you have 5 blocks on your graph, it is nothing but 5 meters, because one block represents 1 meter. So this is how the scaling helps us, and we are all quite familiar by now, I hope. So we'll look into this topic now. So now, as we have already been introduced about going into the third module, where power and delay are very much important, we'll go into the introduction before beginning. After learning about fabrication, which was dealt in the first module, the requirements are in terms of speed and power for a good chip. So ultimately you have to have the best of the speed and the power, and these are very much influenced with the wires. Wires are very much used in our design, which will carry the information from input to the output, and at the same way and at the same time from the power to the device, from the mains to the device. So wires play a huge role. Therefore you have to design the wires in such a way that it occupies less wiring and lesser space. So this is taken care by a design engineer, and if the engineer is a mediocre, normal or moderate engineer, he will completely rely on the computer tool and he will give you the design. But if the person is an outstanding engineer, he will develop his own physical intuition, he will do his own design. Therefore, we are primarily concerned with the development of simple models that will assist us in understanding simple system performance. So later on this can be implemented, but right now we will play with the simple models. So the focus is on the logic and the circuit optimizations of selecting the number of stages of logic, the types of gates and the transistor sizes. In order to use lesser wiring, you need to simplify the logic, and as a result the circuit has to be optimized, and therefore whatever the stages are there, that also indeed has to be reduced, and the number of gates and the type of gates, so that it occupies lesser space, and wirings are also made simple. So therefore this is what is the requirement, and to understand better we will begin with the transient response of an inverter. So transient response is not just got directly, you need to have a differential equation for the voltage, and that in turn will help us to calculate the delay. So as I have already told you that the focus is on designing the simple model. Therefore we'll simply consider the first most simple model, that is the RC delay model. So this approximates a switching transistor with an effective resistance. Whenever you have an RC model, it requires the device to be replaced with a switching transistor with a resistance, and that helps us to provide or estimate the delay rather than complicated differential equations. So of course whenever we want, we should generally use the differential equations to calculate the delay, but that is more complicated, and therefore we go for the better model, which is the RC model, which helps us to calculate the propagation delay in a much simpler way, and this is how it goes on in future. And the definitions given here are as follows. So before we begin with the next topics, we need to understand few of the technical terms. To begin with, we have the propagation delay time. So as we all know, propagation delay time is the time required for the information to move on from one node to another node. This is the generalized equation, but here when we talk in terms of VLSI, we need to be more precise in defining, and it is in this way defined as maximum time from the input crossing 50% to the output crossing 50%. So you can't just initially you can't take simply the start time and the end time. It is, you have to consider the time when the input and the output has achieved 50%, somewhere in the middle. because the responses are not instantaneous. They might consume little time, therefore you may have the transient responses. So that is called as the propagation delay time. Next we have contamination delay time. So what is contamination delay time? It is suffixed as CD. Therefore, TCD is the minimum time from the input crossing 50% to the output crossing 50%. So, initially it takes little time or to initialize the process. So, that is the minimum time for the input to go towards the output, that 50% of the input and 50% of the output. Similarly, when you off, the time taken for the complete device to go into off, that is also called as a contamination time. Next we have rise time. So time taken to go from 0 logic to 1 logic. This is the generalized definition, but here we have to be more precise. Therefore 20% to 80% of its steady state value input starting from 0 to 100%. So 0 to 100% is not considered. Practically we talk in terms of 20% to 80%. And similarly fall time is the fall waveform falling from 80% to 20%. Next we have edge rate, TRF. This is the average of the rise time and the fall time. So these are more precise in looking into the graphical representations. So we have rise time, propagation rise, therefore 0.5. So from here to here is your propagation rise time. And from here to here is the propagation rise time. If you be more specific, so the moment from here to here is your propagation fall time, and from here to here is your from 50% to 50% output, it is your propagation delay for rise time. And these are your rise times and fall times, 20% to 80%. 80% to, so this is your fall time, falling from 80% to 20%. 20% to 80% is your rise time. So when an input changes, the output will retain its old value for at least the contamination delay. As I told you, the moment you switch off the device, it will take little time to completely come to a zero state or a stable state. So that is defined here as a contamination delay. So the delays for the output rising is TPDR or TCDR, and the output falling is TPDF or TCDF. So TPDR, rising propagation delay, that is the input rising to from input to rising output crossing VDD by 2, as already defined, it is half of it, 0.50%. These are the different definitions meant for the already defined definitions. In alternate way you can define this. And the rise time by fall time are also called as slopes or edge rates. So the time is also called as rise time or fall time is also called as, in other ways, as slope or edge rates. Propagation and contamination delay time are also called as maximum time and minimum time. So time required is how fast it goes from input to the output when it has reached 50% is the propagation time. How much slow it goes, that is how to begin with, from what to where, that is called as the minimum time required. The gate that charges or discharges a node is called as a driver. So a driver is nothing but a device which is going to enhance the operation of the next device. The other device is a bit slow, therefore the strength of that device is given by the previous device. So the previous device here acts as a node, the previous device acts as a driver. And the gates and the wire being driven are called as the load. So whatever you see at the output side, they are called as the load. Propagation delay is also called as delay. So TCDR, rising contamination delay from input to rising output crossing VDD by 2. Falling contamination delay from input to falling output crossing VDD by 2 as already defined. Next we have timing analyzer. Timing analyzer is something which is going to compute the latest time at which each node will switch. So the nodes are classified here as inputs, outputs and internal nodes. The user must specify the arrival time of inputs and the time data is required at the output. So we are talking about something new term which is called as an arrival time. Let us see what is an arrival time. Arrival time is the time user must specify the arrival time of inputs. So how much time taken by the input at the required output. So that is in turn defined here as AI, A suffix I. I here in turn is nothing but the internal node, which depends on the propagation delay of the gate driving and the arrival times. So this is the definition, or this is the formula meant to calculate the arrival time. AI is the arrival time, which is given by maximum of j belonging to fan in of I. So I has already been defined as node. To that particular node, how many inputs are supported is called as fan in. If two inputs are there, then we can say j belonging to 2. So the j value is 2, and that in turn is given by aj. Aj here is 2 plus tpdi. I is respectively how many nodes which are present at that particular node. Let us now look at an example of understanding how this formula is implemented, and that in turn helps us how to calculate the arrival time. So what exactly is the purpose of timing analyzer? Timing analyzer computes the arrival times at each node and checks the outputs arrive by their required time. If there is a delay in that particular path then or in that particular node, then that can be rectified, or if that is really not required, that can be completely eliminated. This is how our design becomes more better, or in other words our design is optimized. Therefore it is very much required for us to understand the arrival time. Next we have another definition called as slack. Slack is the difference between the required and arrival time. So I want an information to be passed within 1 second, but it is not happening within 1 second. It can happen for either 1.2 seconds or 0.8 seconds. Then the difference between them is plus minus 0.2 seconds. So positive slacks means the circuit meets timing. Positive, yes, 1 minus 1.2 or 1.2 minus 1 will give you 0.2 as a difference, that is in turn plus, and therefore it has reached, because my purpose was to be meant for 1 second. Sorry, my purpose was meant to be 1 second, but it is taking 0.8 seconds. Then in that case, if it is 0.8 seconds, it is plus 0.2 and it is meeting the requirements 0.8. So 0.8, 1 minus 0.8 is positive slack, whereas 1.2 minus 1 is negative, 1 minus 1.2 is negative slack. Therefore it is not meeting, instead of 1 seconds it is taking 1.2 seconds. So that is negative slack. So the circuit design is not good enough or fast enough. We need to improve that. Therefore arrival times and propagation delays are defined separately for rising and fall transitions. So for two different operations we need to analyze for the arrival time and the propagation delay in terms of rise time and fall time. So the delay of a gate may be different from different inputs. So what exactly is a timing operation? We'll solve the problem based on the arrival time little later. So timing optimization, how to optimize the timing, how to overcome the unwanted delay, and that is focused with respective to 4 different dimensions. So in most delays there will be many logic paths. So these paths are already fast enough. However, there will be a number of critical paths that limit the operation speed of the system and require attention to timing delay details. So the critical paths can be affected at 4 main levels. So for 4 different levels we need to understand the timing optimization, and as I have already told you, so the first one is at the architectural level, at the logic level, the circuit level and the layout level. So what should happen at the logic level, what should happen at the circuit level, that has to be focused. So what exactly you mean by architectural level, what should we do, how should we take care of that? At architectural level we will see, and then later we move on to logic level, circuit level and layout level. So architectural or micro architectural level. So the best is achieved by good micro architecture. Yes, if the best of the best architecture you have, and if you have the best of the best algorithms and the technology, then everything is wonderful. So you can hit the target. But we have some flaws. How many gate delays fit in a clock cycle, how quickly addition occurs, how fast memories are accessed, and how signals like to propagate a wire. So these trade-offs should be taken care, and therefore in order to avoid delays we need to go for pipelining. So what exactly is pipelining? At a time you give multiple tasks. That in turn is called as parallelism or pipelining, and as a result that will help us to do multiple things at a same time, and that in turn will take care to one extent of reducing the delay. So trade-offs at the micro architectural level include the number of pipeline stages, the number of execution units, and the size of memories. It also helps in reduction of the memories. Next, we go at the logic level. So what exactly should be done at the logic level? Trade-offs include types of functional blocks, the number of stages of gates in the clock cycle, and the fan in and fan out of the gates. So at the logic level, how will you design the circuit? Number one, you have to control with the inputs and the outputs. More the number of fan in. What exactly is fan in? The node which accepts how many inputs. A node, if you say a node accepts, for example, if a node accepts, this is a node, it accepts 3 inputs, 1, 2 and 3. Then fan in is 3. Then in that case we say fan in is equal to 3. It accepts 3 inputs. This is the node. This is the node. Similarly, what is fan out? Fan out is you have a device. So this is the output. This is the output. Alright, this is the output. Let me call this as V out. Okay. Let me call this as V out. This is supporting how many inputs? I have 1 input, 2 input, 3 input. So let me call this as input 1. Let me call this as input 2. And let me call this as input 3. So now this device is supporting for 3 inputs. Then we call this as fan out. F out, which is equal to 3. So the device, that output which is got, no, V out, it is supported with some device. So that device is called as a driver. So this is called as fan in and fan out. So the transformation from, though this also should be recorded, the number of fan ins, if you consider, a gate will definitely support any number of inputs, but the speed is going to fall. Therefore, appropriate inputs should be supported. So most of the logic families support maximum 4 inputs, and there also there is a delay. Therefore, normally whenever we give some examples or we talk about examples, it is considered with 3 inputs. So the transformation from function, so we are talking in terms of the functional block or the number of stages. So function to gates and registers can be done. Okay, how will you consider that this is going to create a delay? This is simple. It is calculated in terms of experience of a person. He or she will know that if you have this much of fan in, this much of fan out, the device is going to experience a delay. Or by experiment or by synthesis. You have to generate and see. You have to run and see, experiment. So however, no amount of skillful logic design can overcome a poor architecture. Of course, you should have the best of the best architecture. However, if the architecture is bad, how much ever skilled the designer is, he will not get a wonderful result. Therefore, it has to have a proper architecture and the skill, and only then things will go along. At the circuit level. So the delay can be tuned at the circuit level by choosing transistor sizes. So at the circuit level, how this can be done at the circuit level? You have to choose size of the transistors. So what exactly you mean by size of the transistor? Try to consider the unit transistor. Try to have length and width constant, very less 1 unit, and that helps us to have a reduction or better design in terms of circuit level design. Next, the layout level. So everything completely after your design is done, it's the layout. What is it you come across in the layout? The thickness of the wires and the spacing and all such things. So what exactly happens in the layout level? It is the floor plan which determines the wire lengths that can dominate delay. So when you have the floor plan of the layout, you know how much wire it is going to consume. So if you have good cell layouts, there can be a reduction in terms of parasitic capacitance. Parasitic capacitance, as the name itself suggests, it is an unwanted capacitance that has to be removed. So how do we do this? A common design practice is to write RTL code, synthesize and check the results. So this has to undergo an experimentation, and therefore you have to do it in register transfer level. You have to write the entire design in RTL and try to synthesize the circuit and run, and that will help you to find out whether the layout is having a good propagation speed or there is a delay, and then you can change whatever you are supposed to change. So timing analyzers are used to check the timing closure, and this helps us to understand the timing concepts also. However, without understanding the lower levels of abstraction where the synthesizer is working, he will not understand. So right from the scratch, everything should be known. You know only one concept, you can't be successful. You have to be good in all the things. So this is an arrival time example. Now what is exactly this question is, you have gates 1, 2, 3, 4, 5, 6 and you have 6 inputs. So input 1, input not, input 1, 2, 3, 4, 5, 6. 6, 1, 2, 3, 4, 5, 7 inputs. Okay. And you have arrival time here is given for one particular input I0 as A0, which is equal to 20. Similarly, second input I1, which is equal to A1, which is equal to 30. I2, which is equal to A2, arrival time A2, which is equal to 50. Like this, each and every arrival time for the inputs has been given here as 20, 30, 50, 20, 20, etc. Next, you have one gate. So this is your NAND gate. This is your inverter. So everywhere you have gates, and each gate has a number inside, and this number represents the propagation delay of that particular gate. For example, you have first gate which represents a number as 30. So this 30, this number 30 is the propagation delay of this particular gate. Similarly 20 for this particular gate. Similarly here. So every number represents the propagation delay of that particular gate. Right? So this is sufficient for us to understand. Now how do we get A7, A8, A9, 10, 11, 12? That is how is based on the formula AI is equal to maximum of J is equal to fan in of AJ plus TPI DI. So if you can go along as per this formula, it is better for you to understand. Otherwise, I also will tell you what is the simplest and the right approach. It cannot be called as a crude approach. Though it is crude, it is the right approach. Okay. Now we will consider first one AI maximum. So for this particular 7, A7, how is it you are getting the output? AJ. What is J? J is fan in to this particular gate. How many inputs are there? 2. So AJ is A2. What is A2? One is A1 and A0 and A1. 2 inputs. Alright. Out of these 2 inputs, A0 and A1, which is the maximum? Which is the greatest out of 20 and 30? Out of 2 inputs, J fan in is fan in. 2 input supported is I0 and I1. That in turn is nothing but A0 and A1. So out of A0 and A1, which is the maximum? 30. So this output, therefore, this can be written maximum of this inputs 20 and 30 is 30. I hope I am clear. Fan in of input. How many inputs are supported with this particular gate? 2 inputs A0 and A1, and that is suffixed to J. So what is the maximum of J? Out of 20 and 30, what is the maximum? 30. This has to be added with TPDI. What is your I? This particular one which we are considering. Okay, this is your gate. So if I want to call this as 7, you can call this as TPDI 7. 7. Therefore, the propagation delay of the gate is 30 and this happens to be 60. And this happens to be 60 which I have got here. Similarly, next case, one input. So the output of this, what is A8? Since this has only one input, since this is an inverter, it accepts one input and gives one output. So the input is 60. 60 plus 20 is 80. So A8 is equal to 80. Next you have another gate. So in this gate you have 2 inputs. One input is A8 which is 80 and the other input is A2 which is equal to 50. So the input for this gate is 80, input for this gate is R 80 and 50. So implement the formula. Who is greatest of 80 and 50? It is 80. So 80 plus 30 is 110, and this is your A9, or in other words, since there is no other further network, this is also called as O9 or output 9. On the same grounds, this is also calculated. So you have 60 here and 20 here. 60 is considered. 60 plus 30 is 90. Then here you have 90, you have 20, here you have 60. So it is 90 plus 50, which is 140. So this is how we are able to calculate the arrival time. Next, there is also one condition. So input to the first gate is, okay, as I have told, the same thing which I have written, propagation delay. Now, if your arrival time is 200 picoseconds, what is the slack? If your arrival time is 200 picoseconds, what is the arrival time? So we will consider the same circuit again and understand. Now we have the condition that if the arrival time is equal to 200 picoseconds. If the arrival time is equal to 200 picoseconds, what is the slack? So slack is the difference between the required time and the arrival time. Alright. So now when you look into this, you have 110 and 140. Okay. So what is the arrival time? We have to consider the maximum of this. Therefore, the arrival time in this example is equal to 140. Arrival time in this example is equal to 140. Now, what is the definition of slack? Slack is arrival time minus required time, or required time minus arrival time. So, what is the required time we have? The condition given to you is if the arrival time is 200 picoseconds. That in turn is nothing but the required time. So, if it is 200 required time, but what is the arrival time? Practically, as we have seen, it is 140. So, the difference of this will be 60. Therefore, the slack is 60 seconds. So, this is how we can calculate this also.